Okay, we are starting our unit on weather. So our essential question today is, how does the transfer of energy in the atmosphere create movement of air? This goes with learning target 32. Describe how heat energy is transferred in our atmosphere to create temperature differences in our atmosphere. Okay, so let's first take a look at what our atmosphere is. It's basically a thin layer that forms a protective covering over Earth. The composition of our atmosphere is 70% nitrogen gas, 29% oxygen gas. Now there's other things in the atmosphere besides the gases. There's solids like dust, salt, and pollen. There's also liquids. Water can be in a liquid and a gas form in the atmosphere. Okay. So when we take a look at the atmosphere, we want to look at pressure. Pressure is there because gravity pulls mass toward Earth's surface, and because gravity, the force of gravity, pulls any type of matter toward the Earth's surface, it creates pressure. More dense air near the sea level, more pressure. So let's take a look at what that looks like. Okay, this is an animation of Boyle's law. It shows the relationship between pressure and volume. If you notice, looking at the graph over here, this is an inverse relationship or an indirect relationship. If you increase pressure, volume's going to decrease. And you can see that right here. As we increase pressure by adding more of the green weights, the volume of the matter decreases. And just like when you decrease pressure, take away the pressure, volume will increase. So the relationship between pressure and volume is an indirect relationship. As pressure increases, volume decreases. So let's see how that works in our atmosphere. So when we're at sea level, there's more pressure. There's more gases that are getting pulled down by the force of gravity. And if we take this volume of air, it could be anything. The arrows represent the amount of pressure being applied at sea level. Then as we increase in altitude, and so as we go up in altitude, okay, there's less air pressure, so volume increases. This is why if you buy a bag of chips down in Denver and you take it back up to you in Gilpin, the bag increases in volume and sometimes it pops. Now, temperature is talking about how much energy air molecules have. So hot air has more energy, more kinetic energy. And this is actually what's going to help us create clouds. And we'll talk more about cloud formation a little bit later. So hot air has more kinetic energy, it has more movement. Because of that, because those molecules are spreading around and moving really fast, those molecules are not as packed closely together. Their volume spreads out. So hot air is less dense and it rises. Cold air, which has less kinetic energy, those atoms don't move around as much, they come closer in together, they have less energy, less motion, so they're more dense and they sink. So cold air sinks. Now, heat is a pretty big, important idea that we're going to spend a lot of time talking about. A lot of times you think of heat as in terms of how hot something is. Well, that's actually temperature. Heat is a transfer of thermal energy from high to low. So what that means is it's talking about how thermal energy can move. So for example, if you're at a restaurant and you order a cup of hot chocolate and your friend orders a soda, if you leave the drinks alone, over time, the thermal energy from the hot chocolate will move because that has the most thermal energy. It will actually move across the table to the soda that has less thermal energy, and that's called heat. That's when thermal energy moves. You feel this all the time when you stand near a fire. The fire's really hot. You're not as warm. The air near you is not as warm. So you feel that as heat because that's thermal energy moving from the fire to you. So there's different ways that energy can be transferred in our atmosphere. And that's, remember, what our main target is about, is how does energy gets transferred into our atmosphere. We already know one way is that hot air rises and cold air sinks. And that's actually called convection, which we're going to get to. So there's three main ways that energy is transferred in our atmosphere. The first way is through conduction. Okay? Conduction is energy that is transferred through contact. So the matter that is transferring the energy has to make contact in order for conduction to work. So in order for this, an example of conduction would be if you touch a hot plate. That energy from the hot plate is going to transfer to your hand. That's why we use hot pads when we pick up hot plates. So conduction has to have contact in order for energy to be transferred. Radiation is another way that energy is transferred in our atmosphere. Let me back up for a sec. To give you another example, so when we receive sun's radiation, energy from the sun, and it comes through our atmosphere, that energy from the sun will actually make contact with the ground, with surfaces, and that's what you feel when you feel the hot pavement. You're feeling the sun's energy being transferred by direct contact, which is conduction. Another way that energy is transferred in our atmosphere is through radiation. So this is basically how energy from our sun reaches the earth. Its energy is transferred as waves. So remember, a wave is something that carries energy. We've learned that already this year. And solar radiation travels in space to Earth as waves. That's called radiation. So all the energy we receive from our sun is basically being received by radiation. And another definition is energy passing from one object to another without a connecting medium. With conduction, you have to have matter to conduct. That's the medium that will conduct that energy. In radiation, you do not. Waves can travel without a medium, and so light waves can travel that way from the sun. Now, the last type of energy transfer is convection, which we've already mentioned. This is energy is transferred as warm air rises and cold air sinks. It creates a current, just like in the mantle with magma movement. Remember when we talked in 7th grade about how we have plates, our Earth's crust is cracked into plates, and those plates move because the crust sits on top of a mantle which moves, and the mantle moves because of the convection currents. Remember, hot magma rises, cools, and then sinks, and because of that convection current within the mantle, the magma, our crust moves and it's broken into plates. Well, this is how weather gets created, is through convection currents. So let me just kind of show you a presentation to remind you about the magma for convection currents. So remember, these are our plates. That's what is represented by the green. So because the magma, which is in red, you've got this convection current, hot magma rising, gets cold and sinks. We've got our plates in green. That's our crust. It's been broken into plates, and because our magma and our mantle moves, it creates plate boundaries colliding, forming mountains, plates pulling apart, creating new sea floor. So convection currents not only happen in magma in our mantle, but they also happen in the atmosphere. So warm air will rise, cold air will sink. This convection current is one of the ways that weather is created here on Earth. Okay, show you some more examples of conduction, convection, and radiation. Conduction, you've got energy being transferred by direct contact from the pot to the stove. You've got energy being transferred by radiation. That's when the thermal energy from the hot stove is being transferred as waves from an area of high energy, high thermal energy, to low energy. That's what you feel as heat. Then we've also got warm air rising up to the top. The cap feels that warm air. It gets colder and it sinks, and it will create a convection current. Okay, some other examples of how energy is transferred in our atmosphere. Again, conduction through contact of a medium. Convection, warm air rises. Radiation, energy traveling as waves. Now, the last two things I want to mention are more particular to our atmosphere. Inside our atmosphere, we have an ozone layer. It's O3, so 3 atoms of oxygen bonded together. That ozone layer protects us against the harmful radiation from the sun. So remember, all of sun's electromagnetic radiation travels as waves and goes and hits Earth. Our atmosphere is what protects us from the most dangerous parts of that solar radiation. Okay, so this gives you a kind of a picture of how this works. Ozone and oxygen atoms are continually being interconverted as solar UV breaks ozone and the oxygen atoms react with another oxygen molecules. Okay, so if a UV radiation breaks those oxygen molecules apart, they'll reform again. So let's start with 1. Oxygen molecules are put together. They yield 2 oxygen atoms. This is a very slow process. Okay, when UV radiation from the sun hits those oxygen atoms, okay, they become even more interconnected, and we have O3. That when that happens, that converts the UVA radiation into thermal energy, which doesn't harm us. However, there is an issue with our ozone layer that we've done a pretty good job of stopping. That's the use of CFCs. Those are chlorofluorocarbons. Those are chemicals which we call air pollutants that can kill ozone. And if that happens, then we have no protection against UV radiation. So CFCs are released into the atmosphere. They rise in there. They break down the ozone, and that's not good for us. So we've banned a lot of products that contain CFCs. Hairspray used to contain it. Okay, the last thing we're going to talk about is the Coriolis Effect. Because the Earth rotates on its axis, which we learned from our space unit, this causes the air to move and turn to the right in the northern hemisphere and then left in the southern hemisphere. So this helps also create the weather. Now, this link is a link to the Coriolis Effect. It's also on the website. It'll take you through, it's kind of long, so I'm not going to go through it with you. I would, however, like you to go to the link on the website and read about the Coriolis Effect. So please make sure you do that, and you can add that to your notes. Okay, another thing I wanted to show you is one of the reasons why planes have to fly at a curved direction, okay, because if you were trying to get from starting to end point, because the Earth rotates on its axis, if you went on a straight path, you would actually miss your target. So that's why planes actually have to fly at a curve. They have to fly up and around to hit that point. So if you take a look at this one, you would miss it again if you go on a straight path because of the rotation of the Earth's axis. So the only way to hit that target is to fly in a curve, so you'll land where it lands due to the Coriolis effect. Okay, so that concludes our notes on how energy in the atmosphere is transferred to cause movement of air. So we've got Heat being transferred as conduction, convection, and radiation. That's one way that energy gets transferred in our atmosphere. Another way that energy is transferred in our atmosphere is through the Coriolis effect. The ozone layer also will convert UV energy to thermal energy in our atmosphere. So hopefully you have a better understanding of how energy can be transferred in our atmosphere to create temperature differences, which is basically our heat movement.